Welcome to the AI4EU Cafe for live presentations around AI. Today, live presentation is themed Face De-Identification for Privacy Protection. And our speaker is Professor Pitas. He is the professor at the Department of Informatics of Aristotle University of Thessaloniki, Greece. And he's the director of the Artificial Intelligence and Information Analysis Lab, also in Thessaloniki. My name is Carmen McWilliams, and I'm the moderator and organizer of this online cafe. I'm the director of the company Grassroots Arts and part of the AI4EU project. As always, a small introduction to the rules here. Please take notice that the session will be recorded and no confidential information shall be shared in this cafe session. In this cafe, the speaker expresses his personal view and opinion. This is not necessarily the official AI4EU project opinion. And what is this cafe about? Here, participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and applications. And I'm very happy you're all there. All my participants, please know it's an interactive session. You may ask questions to the speaker, and there is a chat on the right side. You can in there ask your questions, and I read them later to the speaker. And first, before I start with Ioannis, this is the first special AI4EU Cafe on the new project called AI4MEDIA. This is a sister now of AI4EU. There were like 4 projects. They got also funding to be also network projects on AI. Next to the AI4EU, now we also have AI4MEDIA, and we will see more cafe stations now also focused on media. So it's great to have Professor Ioannis Pitas here for the first, and I will introduce him. Ioannis Pitas is an IEEE Fellow, IEEE Distinguished Lecturer, EURASIP Fellow, and he received his Diploma and PhD degree in electrical engineering both from the Aristotle University of Thessaloniki. Since 1994, he has been a professor at the Department of Informatics at the Aristotle University and director of the Artificial Intelligence and Information Analysis Lab. He served as a visiting professor at several universities. He is head of the EC-funded AI Doctoral School of Horizon 2020 EU-funded R&D project AI4MEDIA. He has already 31,750 and more citations to his work and H-index 85+ as a Google Scholar. His current interests are in the areas of computer vision, machine learning, autonomous systems, intelligent digital media, image video processing, human-centered computing, effective computing, R&D imaging, and biomedical imaging. So I now welcome you. Great that you're here. Thank you, Professor Pitas. Great.
Thank you very much
are you?
For the introduction.
Do you hear me?
Yes, sure.
Great. So
thank you very much for the introduction.
Great. I'm giving you now the moderator role. So the floor is you, and we are looking forward to your presentation. Great. We see it.
I suppose that you now see my face and full screen presentation. Is it right?
Yes. Perfect. You're perfect.
Ladies and gentlemen, thank you very much for participating in this lecture. The topic of the lecture is face identification for privacy protection. Why this issue is timely? It is because we cannot really imagine where your private data are. I'm not very lucky because when I search with my name Pitas, I get lots of pita breads. But if your name is a little bit more indicative and you search in the web, you're going to see your faces in many different places. You wouldn't really imagine where they are. Plus, lots of other personal data. Like body images, for example, like the make of your car, or even your car plate can be found with such images, and so on. So the question is how we can protect these images using AI techniques. Privacy, as we understand, is a very important issue, and the European Union took it very seriously and created the General Data Protection Regulation Directive. A couple of years ago, and we are now obliged to protect our personal data and not infringe on people's privacy. So the question is how we can make it feasible, because one of the possible advantages of implementing this EU GDPR directive is to develop technologies that give a sense of a European brand of AI, and hopefully these technologies are going to be used by other countries and big players in the AI arena. So the topic is very timely, it's very important, and the question is how we can deploy AI technology to do our best. We are particularly interested in data protection issues for autonomous systems because they are already around. You see drones flying over your house and taking pictures of you, for example. In the future, we're going to have autonomous cars that have cameras, and they're going to take millions of pictures, and the picture of your car and your face is going to be almost everywhere. So people perceive autonomous systems as machines that infringe private data. For example, drones can overfly private property. So we have to provide tools that can protect the privacy of people and their private data. And of course, we should distinguish when we implement these techniques between actors, because they are public people, and spectators or crowd. And also we should distinguish between public events that can be broadcasted, for example, or private events. So there is a wealth of information. Some of it is to be protected and other not. Regarding now audiovisual shooting, we have data protection issues in broadcasting and in creating experimental databases. As we are a research institution, broadcasters already took privacy protection very seriously, and you see that nowadays increasingly they blur facial images of people. This is a good thing in the short run. In the long run, though, it may have serious implications because all these data are corrupted, and if you store corrupted data and you want to use them in the future for, let's say, training neural networks, then somehow you have to invert these privacy protection mechanisms, and it's not always possible. When it comes to databases, and in particular to audiovisual databases, we routinely collect such data for training our neural network algorithms, for example. The data can be distributed and should be distributed to the scientific community, but they must be anonymous. And facial images, of course, is a primary example of personal data, and the question is, can we really make them anonymous, or can we protect them? How are we going to handle with soft biometric issues, for example, clothes, tattoos, skin marks, and so on? Regarding data collection, first of all, we have to make sure that we follow the proper GDPR compliant approaches for data collection. For example, once people are involved, then we have to have consent forms for the experiments that we do. Regarding now broadcasting, then broadcasters have a standard AV shooting privacy protection rules that must be followed. So for them, it's a little bit different. When it comes to technical means for facial data protection, we have several possible approaches. First of all is face dead detection. If my face appears in an image, I distort the image a little bit and no face can be detected anymore. And there is another possibility, which is the main topic of this lecture, which is face de-identification. In this particular case, we do detect facial images, but we cannot recognize the faces anymore. I mean, the automatic crawlers that find such images, they cannot automatically recognize faces anymore. And this is typically done by corrupting the facial region in such an image, sometimes very much so. Sometimes the corruption is solid, that is just some pixel perturbations, and the humans can still recognize faces, but the machines cannot. And there are various techniques that have been developed to this end. It's maybe this topic is at least 10 years old. We have simple approaches. For example, we can blur a facial image. We can have reconstruction-based approaches where we have, let's say, a PCA image representation. We throw away some components and then the rest of the image is de-identified. And of course, the big thing nowadays is that neural networks, and in particular adversarial neural networks, can be used for face de-identification. Besides facial images, there are other personal data that have to be protected that exist in videos and images. For example, the full body images or half body images have to be protected either by dead detection, so we don't detect human bodies anymore, or by person de-identification, because the human body image is biometric. Okay, so we have full recognizers. Besides this, it's quite timely to consider also personal object detection and de-identification. For example, how to full car plate recognition, police is not going to be very happy about it, or how we can distort a little bit the car image so the car make is not correctly recognized anymore. Here is an example. We have an original image, and the standard naive techniques is to blur it with a Gaussian blur. We have a little bit more complicated reconstruction techniques that produce more visibly pleasant techniques because blurred images are not really that good. But these are overall naive techniques nowadays. I'm going to show you much more interesting results based on neural networks. So when we do face obfuscation or face de-identification, then we have to fool either the machines or humans. And sometimes we do not intend to fool humans because this is acceptable. If you do some web crawling, you're going to see some images. It's okay if these images are identified by you, but if this is done massively by machines, and machines tag millions of facial images and they store the metadata for eternity, this is much more dangerous. It's a much more serious issue. So the focus of this lecture is on machine recognition obfuscation, basically face de-identification. And if we try to de-identify images against human recognition, then of course we have to hide facial image information, and then humans cannot understand the facial identity anymore by blurring or by adding noise. you see these things in TV these days. Sometimes some of these techniques are extremely naive because, first of all, they can be fully invertible. For example, if we just negate an image and we think that we are safe, we can do exactly the opposite, negate the negation, then we have the clear facial image. So you have to know to use advanced tools for real private data protection. I'm going to give you some definitions on what's face identification. So I don't know if I can, okay, I can use the pointer. So let's suppose that I have neural network system that does face recognition. So it has parameters theta, it has an input image X, and it provides an output label. If X is my facial image and Y is my label, then this is correct recognition. So what we do is we perturb my facial image by some pixels or by small noise or by blurring the image so that when I try to do recognition again, I don't get any result or I get wrong results. That's the same thing from face de-identification point of view. So this is the simple definition of face de-identification. You can go and have a formal definition. This means that you have facial images. They belong, let's say, to 1,000 different persons. This is your database that you use for training deep neural network for face recognition. And if this machine is trained properly, then by putting my image on the recognizer, I get the label Pitas. Now, let's suppose that I just perturb my, just a moment because there is a delay in my pointer. So I can perturb the image by adding noise or by pixelation, or I can transform my image, or I can use generative neural networks, adversarial ones, for example, and if I feed my perturbed image on the recognizer, I get a wrong label. So this is the formal definition of face de-identification. And we have various metrics for measuring how well we do. First of all, we have to lower as much as possible the one classification accuracy of the face recognizer. So let's say I have a trained recognizer, it gets 95% recognition for my images. I perturb my data, and then the recognition performance drops to 5%, 2%. That's good. And of course, it's sometimes important that the de-identified image looks like a facial image and looks similar to the original image. For example, if I'm an aged person, then the identified image is good to be of an aged person as well. If we add noise to the image, then we can use the mean square error for measuring the noise. The less noise we need to do the identification, the better. And we can use even more complicated image quality metrics, because MSE is not really good quality metric, but CWSSIM is a good quality metric that has been extensively used in image compression. We can use it here. And here what you can see about the acceptability of image quality of an de-identified image. If an image is blurred, then it's typically not acceptable. There are cases where we can have much better de-identification with much less perturbation. And there is a compromise, because If I start perturbing my image, then I can fool the recognizer, but at the same time, the image quality lowers. And we have an acceptable range, and we have also an unacceptable range where the image quality drops so much that the identified image is really garbage. There have been many face identification techniques so far. Some of them were ad hoc. For example, we can mask the facial regions and blacken them. We can blur them. We can add noise. We can swap face regions from other individuals. Or we can do severe image subsampling, and then we have pixelation of the facial region. The thing of these naive techniques is to blur or blacken or darken the facial image, and the result is not that pleasant, though we typically use such techniques these days on TV broadcasting. You can typically see blurred videos in TV broadcasts these days. We are still using naive techniques for face identification, body identification, as a matter of fact. And then we have other techniques that use modified face reconstruction methods. We can use, let's say, PCA or MDA or ICA or NMF to reconstruct an image. We can throw away some of the components of those representations, and then the rest of it is good enough for face identification. For example, let's suppose that we have an autoencoder that I'm going to talk more about it soon, or SVB or PCA. I modify the coefficients of these representations, and here is my original image. If I throw away some components, this is the identified image. Still, the results are not really that pleasant. They're better than blurring, but not that good. So the main drawback of the original face identification techniques is that they strongly affect the facial regions. For example, you see here the classical techniques that is used by police. We just blacken the eye areas, but then this means that the resulting image is of no use anymore, not even by humans. And we have some desirable properties of the face identification techniques. For example, the identified images should sometimes be recognizable by humans, and they should retain some original face characteristics. Good, for example, if they retain race information, gender information, age information, facial pose and expression, and so on. We can do this these days. Here you see an example of face identification in videos. There are two persons, students of mine. One is supposed to be an actor. We don't protect his face. The other one is supposed to be an audience, so we blacken the face. This is a typical technique that we can use. Here we have another example, again, of an experiment that we have done. I think that I have a problem with my pointer to run this video because sorry, I cannot run this video because the pointer is in another mode. Here we just blur the images. The big family of techniques for face identification is based on autoencoders. Neural autoencoders is a very well-known technique. for image representation these days. Essentially, we start with data sets. These are facial images. We have thousands of them. We feed them into an autoencoder, and then the system is trained. Basically, we map an image on itself, and we have intermediate image representations that are compressed. If we start throwing components from this intermediate encoded feature map, then we can start having lots of information. This means that the similarity of the output image of the autoencoder is not that close to the original facial image anymore, which is good from a facial data identification point of view, if we do it properly. And now let's suppose that this is my image, I have encoded it, and I have a vector of 1,000 features in the middle, and I want to map my image to Carmen's image. Okay, I get the image of Carmen, I pass it through the autoencoder, I get a target vector, and now I have another function that has to be minimized so that I can translate my image into Carmen's image, for example. And we can do it in an advanced way in the following sense. I use, of course, my encoded feature vector, but at the same time, I try to retain information from other images that are relevant to my image. For example, I prefer to retain the information in such a way so that my image still looks like an image of a man and not of a lady, for example. And we encode this information on matrix P. So basically, we define sets that have certain relation to the images we want to identify, and this information is fed in an attraction matrix in the phase identification system. We can also do the opposite. We create a repulsion matrix that serves the following term. Let's suppose that we have opposing facial images. It's no use to map my image to other images of mine, because then it's not identified. So the other images of mine are opposing images. So I incorporate this information in my representation scheme, and I optimize, and the results are very good. Here, for example, we have original images. Here we have the results from standard autoencoder techniques for face identification. These are some results that we obtained. Of course, we cannot say much from the video that I show you now, but if you go into figures, then you can see that incorporating ethnicity and mood information, for example, into the face identification scheme increases the identification performance. So autoencoders is a big family for face identification. Another big family is GANs. GANs are generator discriminator neural networks. Let's suppose that I start with a facial image of mine, okay? And I want to identify, basically I want to translate it into an image of a black person, for example, okay? I have such a target. So I use the generator to map my image on something that looks like the wrong target image. And this means that I learned how to translate my image to this black person's image. And then I have a discriminator. In the discriminator, I feed my black-like modified image, and it should have the same distribution with the black person's image. Okay. And I do it, and if it's true, then this is my the identified image. I have a face recognizer. I pass it. I pass this image y hat that has been identified on in this recognizer, and if it fails, then I'm fine. Here are some examples of live face identification that has been performed on videos. It's live, so if you use such techniques in TV broadcasting today, then the images are going to be corrupted for machines, so persons are not recognizable anymore, but humans can enjoy a good visual quality. And there are quite a few approaches these days that use GANs for face identification. GANs are a little bit heavy though, communication-wise. They can be used not only for face identification, they can be used also for body identification. So we have segmented body images, we feed them into GAN, we create synthetic body images, and these synthetic body images that are similar to the original ones, they are identified. For example, this way we can remove tattoos, we can change the color of the clothes, and here is an original image, here is a de-identified image. As you see, the visual appearance is quite different. Same thing here. Another approach to face identification is to use adversarial attacks. We know that neural networks, especially deep ones, are quite sensitive to noise, so we can take it into our advantage. We modify our image a little bit, and then we fool our recognizer. I present my image to recognizer, and then it recognizes a bird instead of Pitas. We can do the opposite though. Let's suppose that we have a good facial image recognizer. We can modify the face recognition pipeline to make it more robust to adversarial attacks. So this is a defense. For example, if I have to protect my copyright on certain images, then I should not allow them to be fooled. So, in this particular case, we use deep neural face recognizers, and adversarial attacks can be targeted or untargeted. They can be single step or iterative, and they produce imperceptible facial image perturbation. That's the important thing. Humans can still recognize the face, but not the machines. How this is done? Okay, I have my original image. This is X. Then I have a perturbation vector. I try to minimize it, and I have the constraint that when I perturb my image and pass it through my recognizer, then it's not correctly recognized anymore. How can I optimize such adversarial systems? Well, I use the gradient values of another function. And as a result, I have iterative techniques. So I start with my original image. my image, X, and then I start iterating. So, for a reason I cannot see my pointer. Okay. So I start with my original image in my first iteration. Then I find a gradient. I change my image. I clip my image into the allowable image range, let's say between 0 and 1. And I produce a new image and I continue like this till I converge. And J is the suitable adversarial loss. Since since this is an iterative technique and I have to calculate gradients, it's quite computationally expensive, so it's easier if I use the sine function of the gradient instead of the gradient itself. This can speed up the procedure. However, such techniques, they introduce small perturbations, but we have no guarantee that the de-identified image is going to be similar to the original image. So I modify it. I start again with my original image. I perturb it in an iterative way using the gradient, but at the same time I have a second term that forces me to have a perturbed image that is closer to the original image. So I'm always close or similar to my original image. And we have good results in this respect. We have used the L2 distance metric, this metric that is used as an image quality metric in image conversion, and our technique gets the best results. Here is, for example, facial image, identified facial image, and this is the perturbation multiplied by 10. So actually, the perturbations are really very small. They are distributed all over the image. And so the DNS cannot recognize this lady anymore, but I can recognize her. Another concept that is of interest in the framework of adversarial attacks is the k-anonymity concept. So in this case, let's suppose that I have 1,000 facial classes, 1,000 persons in a database, but I have 10 friends. And it's okay if I de-identify my image in such a way so that with equal probability, the label that the recognizer gets is one of the 10 persons, my 10 friends. So if the system is not attacked, I present my image to the recognizer, it gets the label Pitas. If I perturb my image, I present it to the recognizer, then the label that I get is one of the 10 friends of mine, with equal probability. So this is the k-anonymity concept. And the question is, if I have 10,000 persons, then which 10 persons am I going to use so that I have best k-anonymity de-identification performance? And there is a framework to this that is related to DNMs. Unfortunately, I cannot go into detail because my time is almost over. So I'm going just to present you one more thing, one more problem that is related to face identification, but is different. And this problem is face detection. In face detection, we try to fool the face detector. And there is very little work that has been done in this area. So if we want to do a PhD thesis in this area, it's still open. So what face detection does? We send an image to the system that contains maybe 2 or 3 different facial images. And as an output, I get a class label. For example, is there a face or there's no face, or my facial label, and also it regresses the bounding box of my face. So in face detection or face detection obfuscation, I can either fool the recognition part or the regression part of the detection. And I can fool the detector in such a way so that no faces are detected. This is one possibility. Another possibility is that I detect facial regions, but I classify them into something else, into trees, for example, or birds. And the third possibility is that we detect faces, but their region of interest is wrong. So basically, we try to recognize them later on, then the recognition is going to fail. So that's all. This work has been done in the framework of the AI4MEDIA project, where we have very ambitious goals. We try to create a European doctoral academy for doctoral studies in AI. You are going to hear from us soon because Carmen invited me to give a presentation for our activities. It's going to happen, let's say, in a month or two from now, because we're right at the start. And this is all on my side.
Thank you. Thank you. I sent you a webcam request. Maybe you can put on your camera once more when you see it.
Do you want to share my webcam? Should I press this one?
Yeah, it's like a camera sign. Yeah, perfect. So nice. Yes, thank you very much for this very interesting presentation. We suffering a little bit under sound quality. It's not so super today, but we made it, and thank you very much. And I have a question a little bit about, can you tell us a little bit more about this doctoral academy? What is going to happen there? I mean,
okay, you know that nowadays AI is the big thing worldwide, and there are huge efforts in this area. In Europe, we have lots of investments in PhD education, for example, but the efforts are scattered into French initiatives, Germany, the initiatives, Greek initiatives, and so on. So the European Union provided seed money to pull these resources together. So the idea is to create a European doctoral academy, which we call it AIIA, and it's going to offer new opportunities for PhD students and postdoctoral researchers. For example, hopefully we're going to have maybe up to 40 to 50 universities that are going to join, because they participate already in European funded research in this area. And this means that if each university provides, let's say, 3 or 4 different courses, then we can have a wealth of 100 or 150 different courses, long ones, short ones, on every imaginable topic of AI. And the students from within these 50 universities, or students from other universities in Europe, or even international audience, They can have access to this material in a framework that is, let's say, something like Coursera-like, at a more advanced level, of course, and they're going to be benefits. They're going to benefit out of this offer. At the end, if they have some minimum attendance, let's say 6 short courses in a period of 2 years, then we give an AIIA certificate that they can put it into their CV as the supplement. It's not going to be a degree. It's going to be just a supplement stating that Mr. Pitas has attended 3 full courses and 6 short courses, having so many CTS.
Okay, good.
And besides this, we want to organize student exchanges between universities, between university and academia, have strong links with industry. We're a little bit slow these days because of COVID, but we hope to speed up soon.
Okay, so I think who's interested, please just check for AI4MEDIA. There's going to be a website and information, or you send me or Professor Pitas an email and you will get more information. You have my email anyway from my invitation, so you can send me all your questions. Here, I have one question from our participant, Maria Manone. Interesting topic, she says. A quick question. What if the modified face becomes similar to an existing person? There might be ethical, legal issues. A person, for example, is thought of being in a place where he or she actually wasn't, and so on. What do you think? Is there?
It's a very right and crucial question. So whenever you try to fool the system, you should not fool the system in such a way so that it creates problems to other people. For example, if I have 10 friends and I want to have a 10-friend anonymity model, then I can find the average face, let's say, of those 10 friends and make my image close to the average of my friends, not to a particular friend.
Yes.
This is a solution, but there are other solutions as well.
Yes.
But it's a legitimate concern.
Yes. Can I also ask, what are your typical use cases for your topic? Is it more for
the typical use cases, is when you upload the images in Facebook or anywhere else. Before you upload, you just run a small piece of software, you de-identify them. Your friends can still enjoy those images and those videos in YouTube or Instagram or anywhere, but the crawlers cannot get your ID anymore. So
yes.
That's an idea.
Yes, so it's privacy protection, no?
Privacy protection for in a social media environment. Of course, the same approaches can be used in broadcasting environments as well.
Yes. Okay. Thank you. And now I would like to know, is there any AI project which you think is very exciting? I mean, is in your university, what is in the moment the most exciting project in this area?
Well, we have projects that are related to autonomous systems for AI, and there are lots of different issues related to machine learning and autonomous systems, machine learning and computer vision for autonomous systems, but there are some issues that touch other topics that traditionally are far away from AI and from technology. For example, ethics. How can we develop techniques that have ethical rules? Of course, we can impose ethical rules on any autonomous system. The question is, can you learn, for example, ethical tools? Sometimes we learn knowledge.
Yes.
Why Moses, introduced this commandment of his, don't steal. Of course, he did not have any machine learning capabilities at that time, but maybe if I could think about it, could I find such a rule as a result of training? So is ethics trainable in a sense?
Yeah.
So very important issues. They're very diverse. And they involve, arts and science, and it's very fascinating for me.
Thank you. And then one more question to the academy. As a student, can anybody apply to this? I mean, as a PhD student, or can anybody apply? And
well, the rules are still under development. Anyone can apply. The question is under what terms the courses are going to be offered to him. Ideally, for me, these courses should be for free, for Europeans at least, because European Union funds these projects, but some universities have their own rules, so maybe access is going to be under fair terms. So what fair terms means? Possibly it means the same rules that apply to my own university students, they apply to externals as well. If I provide free courses to my students, then I provide them for free to externals, at least to Europeans. But this is debatable because some universities have business models that we have to respect.
Okay. Yes. So I'm basically now rounding up today's session. We get the last question, and that's basically the question: how can we get more students, more European students who might not yet be so clear about AI? How do we attract them? How do we get more young people into the AI studies? Also in our academy, how do we get?
Well, I think, right now the problem is not the popularity of AI. I think that AI is so popular that, many students try to enter into this field. They try to have a master's degree on AI as a specialization, or they want to have a PhD degree on AI because it's easier for them to find a job later on. My question is, how can we ensure that the AI education they get is up to the highest possible international standards? This is thing number one. Thing number two is that how we mobilize the various resources so that with one effort, instead of educating 10 students, we can educate 100 students, for example, with a little bit more effort at European level. This means economies of scale. And the last thing that we should not really forget is the digital divide. There are less favored regions in Europe. Maybe there are less favored countries in Europe in this domain. Certainly, there are less favored countries in the world, and how we can help them lower the digital divide in the AI arena.
Yes.
And we have to define policies on this, on all these issues.
Yes. I mean, you should be aware that, also in this project AI4EU, there's also they're just setting up this educational space. And I think 3 weeks ago, I had the AI campus here, where they basically do open source education space for, German and English. So there are different initiatives, and I think the whole idea about this project is that they are somehow collaborate.
So first of all, certainly regarding the educational resources, by the definition of the ICT 48 project rules, we have to resort on resort on AI4EU tools to make whatever we produce in terms of software available to the entire community. So we have to cooperate with AI4EU anyway. And at the same time, regarding now the doctoral academy, we do not intend to be in competition with other efforts. Instead, we want to be like an umbrella for any educational activities in this area. So in the future, if somebody from China or West Africa or Greece wants to get a short course on computer vision, for example, instead of trying to find what's on offer, he or she is going to go to AIIA webpage and then see that there are, let's say, 10 courses on offer.
Yes.
And he pretty much like he does nowadays on Coursera.
Yes. Here, really the last of our participants, Sylvia Grand-Paré, and that's really the last. Then, are you working on drones data collection projects or standards?
We did work on, and we're still working on drone data collection. We have a wealth of such data regarding humans, athletes, sports events primarily, but also other data that are more suitable to directly to training neural network algorithms, for example. If anybody in the audience wants to get such data, he or she can send me a message, and then all this data is available to you for free, provided that you sign a copyright agreement, a license agreement.
Okay. So now, as promised, we are ending this session, and I thank you again, Professor Pitas. Thank you very much for being here, and it was a great insight in your topic. And whoever wants to have more information, please contact us. You see still the email on the screen of Professor Pitas, and my email you also have. And now I take back the moderation for me, because I just show you shortly what's happening tomorrow, because tomorrow we're gonna have another presentation. And one moment, let me see. Yes, here, this was now. And tomorrow will be the speaker S. Naola, and he's the coordinator of the Artificial Intelligence in Technica, with his talk on artificial intelligence for making products and solutions smarter. So it would be great if you joined tomorrow. Tomorrow we might have the next president in the US, maybe, I don't know. But so it will be a long night for me, at least. I'm going to be up at the television, so tomorrow I might look different. So I'll try to be with a lot of coffee once more awake tomorrow. So anyway, have a nice afternoon and evening and night, and thank you, Professor Pitas, and bye-bye, everybody.
If anybody has any idea about R&D cooperation on any topic, including privacy protection, he or she is welcome to contact me.
Yes, yes. Thank you. So bye-bye.
Bye.
Closing down.